Hello friends, welcome to our YouTube channel. Today we shall solve a couple of numerical problems on DC transients in series RC circuits. We shall learn how to determine various parameters when a charged capacitor is disconnected from the supply and discharged through a resistor. Problem number 1. A resistor R is connected across the terminals of a 20 microfarad capacitor, which has been previously charged to a potential difference of 500 volts. If the potential difference falls to 300 volt in 0.5 minute, we have to calculate the value of resistance R in mega ohms. Let us jot down the data given. Initial value of capacitor voltage V0 equals to 500 volts. Capacitance C equals to 20 microfarad. Capacitor voltage falls to V1 equals to 300 volts in time T1 equals to 0.5 minute. That is equal to 0.5 into 60, that gives us 30 seconds. When a capacitor discharges through a resistor R at any time instant t, capacitor voltage Vc equals to V0 e to the power minus t by tau, where time constant tau equals to R into C. Using values in the expression of Vc, we get 300 equals to 500 e to the power minus 30 by tau, or e to the power minus 30 by tau equals to 0.6. Therefore, time constant tau equals to 58.7285 seconds. That is equal to R into C. Expression for circuit resistance R equals to tau by C. That is equal to 58.7285 divided by 20 into 10 to the power minus 6. That gives us 2.9364 into 10 to the power 6 ohm, or 2.9364 mega ohm. Problem number 2. A 5 microfarad capacitor is connected to constant voltage source through a resistance of 2 mega ohm. We have to calculate the time taken for the capacitor to lose 50%, 63.2% and 95% of its charge when the voltage source is short circuited. Let us jot down the data given. Capacitance C equals to 5 microfarad. Resistance R equals to 2 mega ohm. Let us calculate the circuit time constant. Tau equals to R into C. That is equal to 2 into 10 to the power 6 into 5 into 10 to the power minus 6. That gives us 10 seconds. Let the initial value of capacitor charge be Q0, that is Qc at t equals to 0 equals to Q0. When a capacitor discharges through a resistor R at any time instant t, capacitor voltage Vc equals to V0 e to the power minus t by tau. Multiplying both sides by C, we get CVc equals to CV0 e to the power minus t by tau, or Qc equals to Q0 e to the power minus t by tau. Or we can write Qc by Q0 equals to e to the power minus t by tau. Therefore, t equals to minus tau log of Qc by Q0. Time taken for the capacitor to lose 50% of its charge T1 equals to minus 10 log of 1 minus 0.5, that gives us 6.931 second. Time taken for the capacitor to lose 63.2% of its charge T2 equals to minus 10 log of 1 minus 0.632, that gives us 9.9967 second. Time taken for the capacitor to lose 95% of its charge T3 equals to minus 10 log of 1 minus 0.95, that gives us 29.9573 second. Problem number 3. A cable of 10 km length and of capacitance 2.5 microfarad discharges through its insulation resistance of 50 mega ohm. We have to determine by what percentage will the capacitor voltage have fallen 1, 2 and 5 minutes respectively after disconnection from its bus bars. Let us jot down the given data. Cable capacitance C equals to 2.5 microfarad. Insulation resistance R equals to 50 mega ohm. Given timings T1 equals to 1 minute, that is equal to 1 into 60, that gives us 60 seconds. T2 equals to 2 minutes, that is equal to 2 into 60, that gives us 120 seconds. T3 equals to 5 minutes, that is equal to 5 into 60, that gives us 300 seconds. Let us first determine the time constant. Tau equals to R into C, that is equal to 50 into 10 to the power 6 into 2.5 into 10 to the power minus 6, that gives us 125 seconds. Let the initial value of capacitor voltage be V0, that is Vc at t equals to 0 equals to V0. When a capacitor discharges through a resistor R at any time instant t, Vc equals to V0 e to the power minus t by tau, where time constant tau equals to R into C. After 1 minute, capacitor voltage falls to Vc1 equals to V0 e to the power minus 60 by 125, that is equal to 0.6188 V0. Fall in capacitor voltage V0 minus Vc1 divided by V0 into 100%, that is equal to 38.12%. After 2 minutes, capacitor voltage falls to Vc2, that is equal to V0 e to the power minus 120 by 125, that gives us 0.3829 V0. Fall in capacitor voltage V0 minus Vc2 divided by V0 into 100%, that is equal to 61.71%. After 5 minutes, capacitor voltage falls to Vc3 equals to V0 e to the power minus 300 by 125, that is equal to 0.0907 V0. Fall in capacitor voltage V0 minus Vc3 divided by V0 into 100%, that is equal to 90.93%. Problem number 4. A 2 microfarad capacitor having leakage resistance R and an electrostatic voltmeter are connected to a 500 volt supply. After disconnection from the supply, the voltmeter reading falls to 250 volt in 15 minutes. We have to find the leakage resistance. When the insulation of a cable is connected across the charged capacitor, the voltage drops to 250 volts in 10 minutes. We have to calculate the insulation resistance of the cable. Let us first write down the given data. Initial value of capacitor voltage V0 equals to 500 volts. Capacitance C equals to 2 microfarad. Case 1. Capacitor voltage falls to V1 equals to 250 volts in T1 equals to 15 minutes. That is equal to 15 into 60, that gives us 900 seconds. When a capacitor C discharges through a resistor R at any instant t, Vc equals to V0 e to the power minus t by tau 1, where time constant tau 1 equals to R into C. Using values, we get 250 equals to 500 e to the power minus 900 by tau 1, or e to the power minus 900 by tau 1 equals to 0.5. Therefore, time constant tau 1 equals to 1298.4 seconds. Leakage resistance R equals to tau 1 by C, that is equal to 1298.4 divided by 2 into 10 to the power minus 6, that gives us 649.21 into 10 to the power 6 ohm, or 649.21 mega ohm. Given initial value of capacitor voltage V0 equals to 500 volts, capacitance C equals to 2 microfarad. During case 1, we have calculated leakage resistance R equals to 649.21 mega ohm. Case 2. When the insulation of a cable R inch is connected across the charged capacitor, capacitor voltage falls to V1 equals to 250 volts in T2 equals to 10 minutes. That is equal to 10 into 60, that gives us 600 seconds. When the capacitor C discharges through a resistor at any instant t, capacitor voltage Vc equals to V0 e to the power minus t by tau 2, where time constant tau 2 equals to Req into C. Equivalent resistance Req equals to R in parallel with R ins. Using values, we get 250 equals to 500 e to the power minus 600 by tau 2, or e to the power minus 600 by tau 2 equals to 0.5. Therefore, time constant tau 2 equals to 865.617 seconds. Equivalent resistance Req equals to tau 2 by C. Using values, we get 865.617 divided by 2 into 10 to the power minus 6. That gives us 432.81 into 10 to the power 6 ohm, or 432.81 mega ohm. As Req is the parallel combination of R and R ins, we can write 1 upon Req equals to 1 upon R plus 1 upon R ins, or 1 upon R ins equals to 1 upon 432.81 minus 1 upon 649.21. Therefore, insulation resistance R ins equals to 1298.4 mega ohm. Problem number 5. A capacitor across which connected an electrostatic voltmeter of infinite resistance and of 10 picofarad capacitance is charged to a potential of 100 volts. After disconnecting from the charging source, the potential falls from 100 volt to 50 volt in 20.8 seconds. When an additional capacitance of 50 picofarad is connected in parallel with the test capacitor, the voltage falls from 100 volt to 50 volt in 55.5 seconds. We have to determine the value of insulation resistance of the test capacitor. Let us jot down the data given. Initial value of capacitor voltage V0 equals to 100 volts. Case 1. Capacitor voltage falls to V1 equals to 50 volts in T1 equals to 20.8 seconds. Let the equivalent capacitance be C1. When the capacitor C1 discharges through the resistor R at any time instant t, capacitor voltage Vc equals to V0 e to the power minus t by tau 1, where time constant tau 1 equals to R into C1. Putting values, we get 50 equals to 100 e to the power minus 20.8 by tau 1, or e to the power minus 20.8 by tau 1 equals to 0.5. Therefore, time constant tau 1 equals to 30.0081 seconds. That is equal to R into C1. Given initial value of capacitor voltage V0 equals to 100 volts. During case 1, we have calculated time constant tau 1 equals to 30.0081 seconds. That is equal to R into C1. Case 2. When an additional capacitance C2 equals to 50 picofarad is connected in parallel with the test capacitor. Let the equivalent capacitance be Ceq equals to C1 plus C2. Capacitor voltage falls to V1 equals to 50 volts in T2 equals to 55.5 seconds. When the capacitor Ceq discharges through the resistor R at any time instant t, capacitor voltage Vc equals to V0 e to the power minus t by tau 2, where time constant tau 2 equals to R into Ceq. Using values we get 50 equals to 100 e to the power minus 55.5 by tau 2 or e to the power minus 55.5 by tau 2 equals to 0.5. Therefore, time constant tau 2 equals to 80.0696 seconds. That is equal to R into Ceq or R into C1 plus C2. Tau 2 by tau 1 equals to 80.0696 divided by 30.0081. That gives us 2.6683. Again, tau 2 by tau 1 equals to C1 plus C2 by C1. That may be written as 1 plus C2 by C1. C2 by C1 equals to 2.6683 minus 1. That gives us 1.6683. Therefore, C1 equals to C2 divided by 1.6683. Using value of C2, we get 50 into 10 to the power minus 12 divided by 1.6683. That gives us 29.971 picofarad. Therefore, resistance R equals to tau 1 divided by C1. Using values, we get 30.0081 divided by 29.971 into 10 to the power minus 12. That gives us 10 into 10 to the power 12 ohm. So today we have solved a couple of numerical problems on transients in RC series circuits. We have learned how to determine various parameters when a charged capacitor is disconnected from the source and discharged through a resistor. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.